let's see, I did assign one homework problem. One of the reasons I haven't assigned more homework problems is that the homework problems in Schwartz are, I would say, inappropriate, most of them.
Did you put that homework on the website?
No, I didn't, and I've even forgotten what it was. I hope one of you remembers.
We can replay the
It's in the
video.
camera somewhere.
Yeah, camera.
One of the videos.
All right, well, let's think about figuring out what that is, and I'll try to think of one or two more homework problems.
Oh, here, I think we were supposed to derive the 2580.
I see.
Does that seem right?
Well, yeah, would be all right, I think that's a, all right, so let us, here, you get 2 candies for that. So derive, what is it, 2580?
Yeah, that's what I underlined it, and wrote derive.
Okay, all right.
Wrote the roll.
So, let's say by next Tuesday, because this is, it's been hanging fire now for 3 weeks, I think. Okay, and I'll try to put it on the web page. I'm also going to try to put these notes on the web page. It's called, the notes are called Masses and the Higgs Mechanism. And it's my approach, which I think is simpler than the book's approach. So let me lead you through some of that, and maybe I'll even start from the beginning. The very simplest Lagrangian, or action density, and since these are my notes, I'm using Weinberg's metric, which is minus Schwarz's metric. Okay. If that's your field, if that's your action density, the equation of motion is, and so we identify this as a mass term. For a boson. Okay. And these are scalars, but for vector bosons, there is a mass term is a similar form. For Dirac field, what we have is minus sidebar gamma A dA plus M psi, and this guy here is mass term for fermion, or spin 1/2 fermion, and the equation of motion is d/ plus m psi. So that's that. All right, for a massive vector boson, action density minus a quarter FAB. Yeah, when I wrote these notes, I was trying to avoid using too many Greek letters because we're not Greek, and so you'll see Latin letters all over the place where you normally used to see Greek letters, and then minus a half m squared AA, and so this is the mass term for vector boson, or spin 1 boson. The equation of motion is dA FAB is m squared AB. So it's a mass. Okay, now We were talking about spontaneous symmetry breaking. Let me just review for you Goldstone's theorem one more time. This will be the third time I've said it to you, maybe the fourth time. On the other hand, there's a confusing aspect to it that I think the confusing aspect means it's good to see it more than once. And the mechanism itself is of extraordinary importance in modern physics. So let's suppose that what we have is minus a half dA phi j minus v of phi, where I'm using phi as a vector of n scalar fields. Phi, phi as phi 1, phi n. This is invariant under the global symmetry. Phi prime j is ojk phi k, as long as this is an element of the group On, the orthogonal matrices that are n by n. And that matrix, by orthogonal we mean O transpose O is the identity. And the reason why I've written it that way is that in matrix notation this is phi prime equals O phi, and so this is something like this. This is a global transformation, so the derivatives aren't acting on the orthogonal matrix, and so something like this is invariant. It's just phi transpose phi. And so v of phi is typically some function v of phi transpose phi, and this is effectively the derivative of phi transpose dotted into the derivative of phi. And if the derivatives don't act on, if the symmetry is global, then we have no problems with that. Now, we know that the potential at its minimum, or at any of its minima, is 0. And the second order derivatives this is actually a mass matrix, and it's, when I write non-negative, what I mean is that it's obviously a symmetric matrix, real, so it can be diagonalized, it has eigenvalues, all the eigenvalues are 0 or positive numbers. Why is that? Well, it's because the potential has a minimum. Now, if we had an arbitrary potential that had no minimum, in other words, was unbounded below, then we couldn't say this. We would have some negative masses. But of course, you don't want potentials that are unbounded below unless you figure out, yes.
I'm just wondering, why is that the mass matrix? Is that just,
All right. Marvelous question. Worthy of a, whoa! All right, that was terrible. Sorry. Okay. Just wondering whether I should switch to big chalk, because this, maybe if I just sort of form a big flat surface, which was very hard to draw. Okay, why is it the case? Because we can write V of phi as V at the minimum or a minimum, plus a Taylor series expansion now. The first order terms vanish because we're at the minimum. And the others in the Taylor series would look like this. All at the minimum, and then they would be phi k minus phi k0, phi l minus phi l0. Plus perhaps higher order terms. But in fact, if the theory is renormalizable, then V in 4 dimensions would have at most quartic terms. So since this would have quadratic terms, you couldn't have more than quadratic in this. So the thing actually terminates like that. So that's what the potential looks like near the minimum. But as I said, that's actually the potential period, not just near the minimum. Everywhere it's that. Because at the minimum, or at any minimum, the first order derivatives vanish. And that's interesting, actually. There is something here that it's a little subtle that I've skipped over. You see, when we say that the derivatives are 0, at a minimum, that's true if we're at a real minimum. But if, on the other hand, we've got one of these Mexican hat situations, which is actually what we're talking about, then the derivative, oh yeah, it's still 0 at any of the minima. That's true. It's still 0. Sorry for that distraction. The first derivative is still 0. The second derivative is not 0. So this is what it looks like. And consequent, and of course the potential in general, it would be then V of phi 0 plus 1/2 m squared KL phi k minus phi k0. So let's get rid of these spurious extra terms. Okay. So in other words, the potential is the potential at the minimum plus this quadratic form here. And what we see then is if we rebaptize the fields, get out some holy water, rebaptize the fields, then this, and then if we diagonalize this matrix, and then just consider the fields, the diagonalized fields, then this would be a sum over each of the particular mass eigenvalues squared times 1/2 times the square of that field, wet with baptismal water. Why? Because 1/2 m squared phi squared is what a mass term looks like.
More of a comment, I guess. But at the center of the hat, the mass is going to be negative.
Sorry, say it again.
At the center of the hat, where the derivative is 0.
Oh, but the center of the hat, the top of the hat, you mean here?
Right. It's unstable, but it's still got a negative mass.
But it's not a minimum.
Okay. But it's a place where the derivative
It's
is
a bloody maximum. Well, it's a local maximum.
Yeah.
It's still a place where the first derivatives are 0, but it's a maximum. Here we're talking about
The true.
phi 0 is a minimum,
Okay.
any minimum. Good question. You earned a third penny. You can soon open a store. Sell them to the others here. Okay. Now, the any orthogonal matrix near the identity is of the form The T's are n by n matrices that are the generators of ON, and the thetas are just real numbers. You wonder, what's the I doing there? Well, this is a physics department. We can't do anything without putting an I in. It's a fetish. It's called a physics fetish. We have another one, it's called H bar, but we set that equal to 1 in natural units. So if we put an I in here so that these are Hermitian. Any sensible person, a mathematician, would leave out the I and make these guys real and anti-symmetric. No. Imaginary and anti-symmetric. And they would be Hermitian. If the T's are Hermitian, the whole thing is real, so the T's are imaginary and anti-symmetric in physics departments. In math departments, you multiply through the I, and you get something that's real and anti-symmetric. So it's anti-Hermitian then, real and anti-symmetric, and you cover up the I, real and anti-symmetric. Physics departments with our fetish to make the thing Hermitian. So much for that. Imagine what I would say if they ever let me teach astronomy. Okay, so partial d of phi, partial theta r. Well, it's called partial d of phi, partial phi j, partial phi j, partial theta r. And this is 0 because we have ON symmetry. So when I say partial d with respect to theta, what I really mean is that phi is, in other words, I'm taking phi to be some 1 plus I theta r tr acting on, in other words, I'm doing that, okay? Or better yet, then this thing really is an orthogonal matrix, whereas this is only valid near the identity. Okay. So in particular here, phi j of theta, I should have written this down rather than. So phi j of theta is phi j of 0 plus I, the generators, for small theta. And so this thing up here is equal to partial d of t, partial phi j, and then partial phi j, partial theta I is I tr jk phi k equals 0. Okay, so this is 0 because of symmetry, the ON symmetry. And now if we differentiate this vanishing quantity, what we get is the second derivative, vector phi j phi k, I tr jk phi k, plus, now we differentiate with respect to that guy. We differentiate with respect to phi now. Well, we differentiate with respect to phi there. But anyway, this term is partial d of phi, partial phi j. That's this guy. I tr j and we differentiated with respect to, well, actually, I decided to use L for some reason. So let me do that. So if we differentiate with respect to phi L, we get JL there, and then over here, we just get second derivative with respect to phi J. Okay. So this is always true because of the symmetry. Now we go to the minimum. If we go to the minimum, the second term drops out, because at a minimum, the derivatives are 0. So that means then that we have partial 2v at phi 0, partial phi j, partial phi L for some reason. Goodness, I switched back to, let's just, this is 0. I TR JK phi K0 equals 0. So that's what this equation becomes when you set phi equal to phi 0. Okay. So what does this say? Well, this, of course, is the mass matrix, which we had previously identified. So this is really saying m squared JL ITR JK phi K0 is 0. Well, that says that the mass matrix has certain 0 eigenvectors. This is then an eigenvector, and it would have, m squared is symmetric, so let me write it this way. Now it looks more like an eigenvector. Okay. And so, as long as this is not 0, then what we have is a massless particle. On the other hand, some generators, or some linear combination of generators, are going to give you, in other words, we're going to have some, let us say, some alpha j TR JK phi K0. Some of these guys are actually going to vanish. And in fact, what I should have had here was thetas. In fact, theta R. So for some thetas, we're going to have, for some linear combination of these, we're going to have that this linear combination is 0, and when that's 0, we don't really get, we don't have an eigenvector, because the vector is 0. And so what that means is that every generator of ON that doesn't leave, every generator of ON that doesn't leave the vacuum, the minimum invariant will correspond to a 0 mass particle. On the other hand, the masses of the particles, the masses of the linear combination of fields that correspond to combinations of generators that leave the vacuum invariant, those guys could have positive masses. And the picture, the physical picture of the Mexican hat is very useful because the generators that take you in this direction just along the trajectory of minima, the circle of minima, this generator would correspond to a zero mass particle, and you can see if this is the potential, there's no resistance here. On the other hand, anything that takes us in a perpendicular direction, that would give us the perpendicular vibrations. They would be non-zero. And so here really we're talking about a circle, and so we're talking about U1, or we would be talking about O2. I guess that's a better way of thinking about it. So we think about O2, and we have rotations this way. They correspond to zero, and O2 really only has one generator. And so the only generator is massless in this case. And the vibration, but there's a second gauge boson, there's a second scalar boson, and it has mass corresponding to those vibrations that way. All right, anyway, I hope I haven't made that too confusing. We can promote a global symmetry to a local symmetry if we introduce gauge fields, and as you know, the idea with gauge fields is that pi plus ai prime on u of x is the same thing as u di plus ai of x. This is an x there, and so what you have then is psi prime I of x is u of x psi, well, when I say I mean I, j, psi of x, and a prime I of x is u of x, a I. Well, actually, I'm screwing up the notation a little bit, so let me fix it. This is just okay. I is a space-time index. All right, so this was the idea of course, Yang and Mills, which was so extraordinarily important. So let's look at the abelian Higgs mechanism. In other words, what happens if we have spontaneous symmetry breaking in a theory with a local symmetry? So since I have some unused blackboard here, I will use it. Minus a quarter FAB minus dA phi star dA phi okay, so phi is, you can think of phi as 1 over root 2, phi 1 plus I phi 2. And so it's one complex scalar field. And the covariant derivative in this case, d b of phi, is the space-time derivative plus i.e. ab acting on phi. All right, we're all happy. So this is the way I've written it with positive m squared. This is a massive charged scalar boson interacting with the electromagnetic field. In fact, this is a theory that Schwartz discussed several times in the early chapters. On the other hand, if we switch this to by putting a plus sign here, then all of a sudden what we've got is the wrong sign. In other words, the potential now, V of phi, is now equal to m squared phi squared minus a half, plus a half lambda. Oh, wait a minute, I've got it backwards. Minus m squared phi, so it's a half lambda, absolute value of phi is 4. All right. And what does this say? This says, well, phi equal to 0 is not a minimum, because as we move phi away from 0 a little bit, we go downhill until eventually the phi fourth starts to play, starts to make itself felt. But for small fields, phi squared is always bigger than phi fourth. And in fact, if the field is small enough, it's a lot bigger. So this is the Mexican hat situation. And the minimum here, what is the minimum? Well, partial v, partial absolute value of phi squared, set that equal to 0, what we get is minus m squared plus lambda phi squared. And so the mean value of phi squared at the minimum, phi 0 squared, say, is equal to m squared over lambda. So that's the minimum, and that's the distance here. M squared over lambda, square root, because that's phi squared. All right, well, the next thing we do is we say, well, we've got a symmetric set of vacua, so let's pick one and expand around it and consider what the interactions are. So we say phi is equal to some phi 0 plus 1 over square root of 2, sigma 1 plus I sigma 2. And phi 0 is what? M over square root of lambda plus 1 over square root of 2, sigma 1 plus I. And we can rewrite that as m over square root of lambda plus sigma, where now sigma is a complex field, but it has a mean value of 0 in the vacuum. So the mean value in the vacuum of the field now is equal to m over square root of lambda, but the mean value of sigma in the vacuum is 0. So that's what that looks like. Let me get a swig of water. Does anybody have a question when I'm near the box handy? This is the best time to ask, because then I can just reach down, grab a candy, and throw it at you. Okay, well now let's look at the potential energy term. V phi then is minus m squared phi star phi plus a half lambda phi star phi squared. And I'm going to skip a little bit of algebra here. It's in the notes. It's an equation 63 that has 1, 2, 3, 4, 5 lines. I'm going to skip that. This is m squared, sigma 1 squared plus square root of 2 lambda m sigma 1 sigma squared plus lambda over 2 sigma squared minus m to the 4th over 2 lambda. Sigma squared here is equal to sigma 1 squared plus sigma 2 squared. So this is our new potential. And so what is our theory? The theory, of course, is L is minus a quarter, FAB, and minus dA phi star, dA phi, and then plus V, plus this V of phi. Now, if we look at it, what do we see? We see that there's a, looking at the potential, this is a D. It's almost, looks like some obscure Chinese character.
And that's a minus.
What?
That's a minus the potential.
It's one?
It's minus the potential because this is the grounded.
Yes! All right, I owe you 2 candies. Two candies. Oh, sorry. Okay, so just looking at this and that and this, what we see is it looks like it has a scalar boson of mass M and a massless scalar boson sigma 2 and an electromagnetic field. That's what it looks like naively. But this term tells us that that's not in fact what's, so this is the parentheses that I somehow left out. So what is this kinetic part of this field phi, which one might call the Higgs field? And dA phi, because this is just the abelian case. We'll get to the SU2 case later. So what is this? This is minus dA minus IEAA times phi 0 plus sigma star, because sigma's complex. And the derivatives stop there. Now we have a new derivative, dA plus IEAA acting on phi 0 plus sigma. Okay. So that's the kinetic action of the Higgs field, the complex field. Now, if we work that out, and I'm going to skip 1, 2, 3 equations. This kinetic action can be rewritten as, well, just notice what's going on here. We have a phi 0 here. We have a phi 0 there. And in fact, for practical purposes, let's remember that the fields are sort of quantum vibrations around 0. Now that we've factored out or subtracted out the phi 0, the sigmas are just sort of vibrating around 0, the gauge fields are vibrating around 0, and so the only thing that's really there in this thing is minus E squared phi 0 squared AA. We took phi 0 to be real, of course. So in other words, minus I, plus I, minus I plus I, plus 1, minus E squared, A squared, phi 0 squared. Well, this tells you that we've got, that this gauge boson has acquired a mass. And the mass squared is m squared over 2, I should say, is E squared phi 0 squared. Because if you look on that front board over there, the bosons, it's m squared over 2 is the mass term. M squared over 2 times the square of the field. And so so m squared over 2 is E squared phi 0 squared. So that's that. And then the rest of it is minus dA sigma star dA sigma minus square root of 2 e squared AA phi 0 sigma 1 minus square root of 2 e AA phi 0 dA sigma 2. And remember that sigma is, oh wait a second, I had sigma squared there. Sigma is, there should be a 1/2 there. Sigma is 1 over root 2 sigma 1 plus I sigma 2. Okay, and by the way, in this computation here, certain things cancel. The linear term in the term linear terms linear in sigma 1 and quadratic in sigma 2 cancel in the potential. And that may not be obvious, but it's true. Okay, so the gauge field has this particular mass, and then it makes sense to rewrite, to define a new gauge field, BA, as AA plus 1 over m dA sigma 2. And that's because you see there's a dA sigma 2 here, multiplying times phi 0 multiplying AA. So this is a cross term. And so if we redefine, if we rename the gauge field B, then what happens? Well, FAB, which of course is dA AB minus dBAA, is also equal to dA BB minus dBBA, because this thing here, which has the form, it's sort of a quantum gauge transformation, isn't it? In a sense, okay? In other words, we're adding the gradient of a scalar field to the gauge field, and that doesn't change the curvature. Okay. So now in these terms, what's the action density? Yeah, in fact, I'm a little worried about running out of blackboard space. I think we're all right. Let me just write it this way. What we have then is minus a quarter FAB minus a half m squared BABA minus dA sigma star dA sigma plus terms that are cubic and quartic. In other words, these are interactions. But these are the terms that tell you what the fields are. In other words, the quadratic part of the thing is that. And okay. On the other hand, we could just write everything in terms of A. We don't have to use B. In any case, what we got is a gauge boson of mass m, a scalar boson of mass little m. And but now here's an important insight. This is a gauge theory. It has local symmetry. So we can choose to think about the theory in a particular gauge. We can choose a gauge. What is the nicest gauge to choose? Well, the nicest gauge to choose is to choose a gauge so that the field phi, which is complex, we make a U1 rotation so that phi is real. So then we choose a gauge which the phi is just phi 0 plus, let us say, sigma 1. Or is it sigma 1 over root 2? Sigma 1 over root 2. So in other words, this is m over square root of lambda plus, and I'll set this now equal to sigma over root 2. So what I mean by sigma is, well, I'm sort of schizophrenic here in the notation. I'm saying that sigma is 1 over root 2, sigma 1 plus I sigma 2. And now I'm saying, well, sigma 1 over root 2 is the real thing. So maybe we better leave it as sigma 1 and just say sigma 2 is gone in this gauge. And what is the theory? Well, the theory then is minus a quarter FAB minus, so phi is equal to this, minus dA phi, it's a real field, minus E squared AA, phi squared, and of course phi squared has a big M there, so this is a mass term, and M squared phi squared minus lambda over 2 5 and 4. So look at it this way, we have the simplest possible kind of symmetry breaking. It's just that this real field phi we can rewrite as m over root lambda sigma 1 over root 2. And okay, so in these terms, what is it? Well, it's minus a quarter FAB minus E squared M squared over lambda AA. I now see that the I've somehow, no, that's right, okay. Minus a half dA sigma 1 dA sigma 1 minus M squared sigma 1 squared minus square root of 2 over lambda M E squared AA sigma 1 minus E squared over 2 AA sigma 1 squared minus square root of lambda over 2m sigma 1 cubed minus lambda over 8 sigma 1 to the 4 plus m to the 4 over lambda. Okay. So that's what the action density is. And what do we have then? We have a massive gauge boson here. We then have one massive scalar field There's no sigma 2. This is called unitary gauge.
So,
I'm not really following Mr. Blasio's advice, but I'm doing the best I can.
no big M's?
Well, what is big M?
Big M is 5 zeros.
Big M is square root of 2 E 5 0, and that's square root of 2 E M
Overlap.
over square root of lambda.
Okay, great. Great.
That was a question, so you get a candy.
Yes.
Okay, so this is the Higgs mechanism. Now, some of you may wonder, well, suppose the mass term wasn't negative, suppose we didn't have any spontaneous symmetry breaking, could we still go to unitary gauge? And here, the problem is that the gauge transformation would be singular in the vicinity of the vacuum, that is to say, where the fields are small. What we would have E theta would be arctan by 2 over R1. And all right, let's not go into the weeds too far. Now, the next thing here in my notes is the ON Higgs mechanism. But I just wonder whether, maybe I'll just give you the bare bones of this, really very, very briefly. Here we have L is minus a half sum I equals 1 to n dA phi I dOA phi I plus a half m squared phi I squared minus lambda over 4 phi squared squared. Where phi squared is, well, this thing is phi squared. In other words, phi squared is from phi squared. All right, so this is one that we were talking about a moment ago. Now the gauge field matrix AB is IE sum on the generators, and here for some reason, I guess because I used A for the space-time, I couldn't use it to label a generator. Over there I was using R. Maybe I can get away with R. I'll change it on the fly. R equals 1 to, it turns out for ON, there are n minus 1 generators. And so this is generator R, AB, R. Okay. So these are our gauge field matrices, and of course we have TRTS is IFRST TT. Sorry about the TT, but what are you going to do? Maybe I should give up my... I'm not opposed to Greece. In fact, I think Greece should... I think the Germans and the EU should cut Greece a lot more slack. Okay, these generators, TRTS is some K delta RS. And we can write the full action of the theory. So this is just the Lagrangian, the action density for the scalar field. The action density for the full field is a quarter trace FIK minus a half dA phi transpose dA phi plus a half phi squared minus a quarter lambda over 4 phi squared. And because FIK here is the commutator of DI with DK. And because, maybe I should say that DI, of course, is DI plus AI. AI means anti-Hermitian things. All right, once again, because of the spontaneous symmetry breaking, we'll imagine that the field is pi 1, pi 2, ... and we'll pick a vacuum that's phi 0 plus sigma. Sigma now is real. The mean value in the vacuum of phi I is then delta IN phi 0. So in other words, all the mean value of all the components of phi vanish except for the last one. And okay, so I guess I'm running out of space and time, so I guess it's sort of a Lorentz covariant expression. Maybe it's good to we'll do the SU2 next time. So the kinetic part for phi in this case is minus a half dA phi transpose dA phi, and this is minus a half, and so now this is the sum on I, K, L, 1 to N, delta I, K, dA plus the sum R equals 1 to, NN minus 1 over 2, IE, TR, KR, IK, A, phi K. So that's that one. And then this one is delta IL dA plus a sum on, let us say, S, IE, TS, IL, A, S, A, so that's the kinetic part of the action density for the scalar fields. And now what happens is, again, imagine the fields all vibrating around their minimum values, and the minimum values are 0 for all of them except the nth one. The nth one has a 0 there. It is phi 0. And so what we've got there then is the following, that this thing is equals, I'll just write it as vibes, okay, plus, and what's left? Minus a half IE TR IK ARA phi 0K and I'm being a little precious here, I-E, T-S, I-L, A-S-A, phi, 0, L, but these guys are all 0 unless K is equal to N and L is equal to N. And so this actually is a half E squared sum on I from 1 to N, TR, TS, IN, IN, phi 0 squared, AAR, AAS. God, you can't read anything. Okay. So, what we have then is a mass matrix, so 5s plus, or rather minus, a half m squared RS, ARA, ASA, and what's m squared? M squared RS is equal to E squared phi 0 squared, and it's then I, TRIN, ITS, IN, and we're summing over I, and we're not summing over N because N is the index that we chose to have a non-zero mean value in the vacuum. Okay, so this thing is obviously symmetric in R and S. So we have here then a symmetric matrix. It's also real. Well, if we got rid of the i's, then these would be. These things are Hermitian. They're imaginary and anti-symmetric. Multiply through by the i's. They're real and anti-symmetric. So this thing is real, and it's non-negative also. And so this is then the mass matrix, and so some of the masses can be 0, and in fact, what masses are 0? Well, if the sum, how shall I say? Suppose there's a generator TH, IK, phi K. Suppose there's a generator like that. And this may be a linear combination of generators, okay, depending on how we define the generators. But for simplicity, let's just rebaptize the generators. So here's a generator that leaves the mean value of the fields constant. Well, what does that mean? That means then that effectively, for the case we chose, THIN is equal to 0 for all I. So one of the generators here, R equal to H, S equal to H, has a 0 mass. Okay. And actually, it's more than one because we're talking ON. So in ON, let me make sure I've got this right now. We've got ON, and there are actually n minus 1, or rather n minus 1, n minus 2 over 2 h's. So there are that many h's that leave the vacuum invariant. All right, let's check this. let's suppose we were talking about O3. O3, we have 2 times 1 over 2 will be 1. Well, that's right, because if we have the Higgs field like this, it's a 3 vector now, a real 3 vector, we're talking about O3, then rotations about the z-axis, leave this invariant, but rotations about the x-axis and about, well, that was actually about the y-axis. This is about the x-axis. Move it. But rotations about the z-axis, leave it unaffected. So these are the number of eigenvalues that are 0. For O4, we would have 3 times 2 over 2. We'd have 3 that would be we'd have 3 massless gauge bosons, and the others would be massive. In the case of O3, which we can visualize much more easily, we have 1 massless, 2 massive. All right, so that's the abelian Higgs mechanism, and there's some more detail. I'll put this on the web page. Maybe we can start talking about the SU2 Higgs mechanism. The difference, maybe I can just, because we don't have any blackboard space left, the difference will be that this A sub B, what will it be? It'll be IE times a half sigma dot A B. Yeah, I see now there's a B missing here. Always another typo. Roaches in the New York apartment. Okay, so we're talking SU2, the generators of the Pauli matrices divided by 2. And remember the Pauli matrices, sigma I, sigma j, delta ij, plus I, epsilon ij, k, sigma k, and let me make sure that I haven't screwed up a factor of 2. There's always a... No, that's correct. Okay. So that's what the Pauli matrices do. And so this would be our anti-Hermitian gauge field written in terms of now Hermitian sigmas. So now the I is, because I wanted it to be anti-Hermitian. That's my fetish. All right, so we'll pick up next time at that point. And does anybody have a question? There may be more questions. I do have a whole box of candy as you know.